Okay, 1, 2, 3. All right, that should do it. Hi, I'm Charles, and welcome to part 24 of the OpenSCAD video series. In this part, we're going to be talking about surface hulls on parametric surfaces. Let's get started. So, we should probably start with what a parametric equation is. Or to do a surface hull on a parametric surface, we need a parametric surface, and to get a parametric surface, we need parametric equations. And so you might ask, what are parametric equations? And we'll have to suffice it to say that a parametric equation is, usually we have an equation similar to this. We say, if we have two variable inputs, x and y, we get some z value. Or we say z is equal to some function of x and y. Maybe we say z is equal to x plus y. Something like that. Or x times y. Or x times x plus y. That sort of thing. So our two independent variables are x and y, and our dependent variable is z. So in a parametric equation, all z, x, and y are dependent variables, and we have new independent variables called s and t. So let me give you an example. Let's say we're going to make some functions to just make everything super clear. So say function x of s and t. This is a function called x, and it takes s and t, and it's going to represent our x value, the x location of a data point or something. So let's say x is equal to s plus t. Okay, so now we can do something similar for y. Let's say it's s minus t. And finally, a function for z. We'll say it's s times t. Just to make, make things interesting. All right. So now we essentially have we've got our functions, and I guess we kind of want to visualize them. So what happens if we give them some values? So let's make a for loop. Say I so what I'm doing here is I'm just defining a for loop, and it starts at -1 and it ends at 1, and we're going to create this variable over here called step 1. So we're going to do the same thing for something called j. So now we have to define step 1 and step 2. Let's say it's 0.1. Keep it simple for now. Whoops, 0.1. There we go. Okay, so now we need to draw some points. I forgot an important function. So an important function that is not necessary for parametric equations, but it's going to make our lives a little bit easier. We're going to call this function p, and it takes s and t, and it's going to return us a vector. It's going to give us back a vector. So it stands for point. So this function gives us the point. It's going to take the x, y, and z functions and turn them into their x, y, and z values. So we'll just put that in like that. It's pretty simple. Okay, so now this point will give us back a vector. Yep, that's pretty much it with all of these things. So we don't have to call them every time that we want to make a new function. We can just call this in our translate statement. So I'll show you what that means. So let's make it capital S, and we'll say maybe it's 10 times I, and capital J, which is equal to 10 times little j. Cool. All right, and now I'm gonna no, never mind. Okay, we'll turn that into t. That makes more sense. Cool. And now we want to translate. And here's where our point function comes in. Capital S and capital T. Say cube. (0.1), same as the step size. All right, pretty basic. So we've got our three parametric functions. We have a function that takes s and t and gives us the vector that corresponds to our functions. We have our step values and we have our for loop, and just changing these values here. And then we just have a translate function. It calls our point function and we have a cube. Okay, let's see what that does. Okay, and we get some points. I wonder if this would be a bit better if it was a little bit finer. We could see more. Maybe I can up the size too. There we go. Okay, so this gives us a shape, just like any shape. And what we're going to be looking how to do in a little bit is how to combine all of them, so it's more of a smooth surface. So let's say if we took away s and t like this, so x is just s and y is just t, it becomes essentially equivalent to just a normal 3D equation. Let's just say s times s plus t times t. This should give us a paraboloid, and it does. It gives us a tall looking paraboloid thing. And what the interesting part is when we when we start changing the other functions as well. So s and t. So if we bring this back, s plus t and s minus t, I mean, it gives us something pretty similar, but it is different. It does ultimately give us something different. It might be more elongated. Let's see. What if I make this s times t and s divided by t? Yeah, that gives us something very different. Or I could just make this s. Yeah, so that's a pretty different function, but still definable by a simple set of equations. Okay, so now what we want to do, the first thing that we're going to do is perform a surface hull. I like this function, so we're going to leave it as is. So right now none of the points are connected, they're just separate, and well, that's not what we want for the purposes of this video and explaining the concept. So I'm going to show you how to hold them together. So I'm going over here. I made some pictures, and here we go. So we have to imagine that we have 4 points. The first point, a point over here, a point over here, and a point over here. So don't worry too much about all the words. I'm going to explain them in just a moment. So we've got 4 points. They essentially make a square and 2 triangles. So if we have 4 points, we have a lower triangle over here, and an upper triangle over here. So we'll call this triangle 1 and triangle 2. So if we look at the main point over here, we can see that it's just essentially the function of s and t. So our normal point, like if we look at any of these points right now, this is just it's any of them. It's fine. Like here we have point of s and t. That's what we want. So to make the triangle, we need to modify the point slightly. So what we need to do is to get this point over here, the upper point, we need to add step 2 to t. We need to take the function where we've added step 2 to t. So we have our function, which is called p, not f, but they're the same thing. It takes s, and then this part here, t plus step 2. So now let's go do that in the code just to show you exactly how that works. So we're going to call this S2. So that's equal to 10 times hold on, let me just go back a second. Okay. No. This is wrong. So that's for this point. So let me go back. So T2. Sorry. T2 will be equal to 10 times J plus step 2. Because J, the relevant step for J is step 2. So to get T2, we need J plus step 2. So what that's going to do is that's going to give us this point over here if we give it S and T plus step 2. So we'll create a new point. Let's call this our main point. And we will call this, what did I give it a name? Point plus step 2. Maybe we'll just call it P.2. And this one can be 0.1 because we're adding step 1, and this one can be 1, 2. Okay, so we'll call this 0.2. Okay, and so we can just copy and paste this section over here. And the important thing that we have to change is from T to T2. So yeah, that's that change. So if we, did I make a mistake? It says I have made a mistake. I did not add a semicolon here. There we go. Okay, if you saw there was a slight change here, and that's just because it's adding an extra set of points that we need. So we can repeat the same thing with S. So if we look at 0.1, we need S plus step 1 because step 1 corresponds to S. We can see here that S is defined by I, and I is defined in relationship to step 1. So S2 is equal to 10 times I plus step 1. There we go. So if we want, now we want to make 0.1. We'll call this 0.1. And we want S2 because we got T2 here in 0.2 and we want S2 here. that essentially takes us to the next place. And so I'll press F5 again, and it generates another set of points you might have seen. Now this is kind of tall. Maybe I'll bring it down just a little bit so that it's a little more visible. Nope, too much. Nope. There we go. It's a little better. Just so we can see it. And if I raise this. Okay. All right, so now we actually have enough points to start our surface hull. And so I want to show you what I mean by this bottom triangle here. So we're gonna we should end up with this bottom triangle. And we haven't generated this point yet, so we won't be able to make this triangle yet, but you'll see. It's very simple from what we already have. So all we need to do here is hull all these points together. And move it over just to make it nice. Save and preview. There we go. So as you can see, we have some triangles, but not all the triangles. And what's interesting, because it's a parametric equations are defining this this shape. On this part, we can have triangles on the bottom, and in this part we have triangles on the top. It's a little strange, but that's just how it is. And I think I'm going to add in a parameter for the cube size, just to make it so that I don't have to change them a whole bunch every time that I change them. Should be able to just, oh boy, gotta make it fancy. Okay, perfect. So I've just made them smaller, so it's more like a surface right now. It's a bit thinner. Yeah, so we have half the triangles, and now we need the other one. So we need to look at this point over here, and we can see by its function to get here, we took a step this way, we took a step this way, and now we need to take both steps. And you can get there either way, but we just need to have the point corresponding to S plus step 1 and T plus step 2. So essentially all we have to do that, we can just copy and paste that. I'm going to call this the lower triangle, or actually, you know what? I'll call it triangle 1 because that's the first triangle, and we'll call this triangle 2. So all we have to do to get the upper triangle, or triangle 2, is to change these both to S2 and T2. So we give them the correct step. So when we do this, this should complete it. It's a little brighter on this side. There we go. And we have a complete surface hull of parametric surfaces. That was simple. And we can change the step size to make it more or less fine, depending on what we want. And it can look a little, maybe it looks a little more blocky now. That's fine, whatever you want. But there are other steps to this process. So as you can see, we've got a surface, but what if we want to add some thickness? Like, what if we want it to have some size to it? So one thing we could do is just change the cube size, but I would say that this isn't. You do get some thickness, but it's not necessarily a very good way to do this, because it's a little unpredictable, and it won't necessarily always give you the shape that you want. I mean, given the method I'm about to show might not always give you the shape you want, but at least it's another thing in your toolbox if you if you want to do this sort of thing. Okay, so I'm going to take it back to being more of a surface. Okay, so I made some more pictures so that I can show you guys what to do. Okay, so I should note that this image and this image are not exactly related. So that's kind of an important thing. There are some common points. Point plus step 2 and point plus step 1, which correspond to this point and this point, but this is kind of an image to itself to make sense of things. So we have our main point again. We want something called the normal vector, and I think it will become clear in a little bit why that is. But to get the normal vector, we need to do something called the cross product of two vectors. So we need a line like this and a line like this, and we need to find the cross product, and that finds a vector, a line which is 90 degrees to both of them. So yeah, we need to do that. So we need to find those vectors. And to find those vectors, we ideally need to find a set of points that let us do this. So we're going to approximate the surface, because actually finding these values exactly requires some calculus. So we're going to do that kind of without calculus. It's similar, but we're just going to do it like this, because this allows you to do it with pretty much any function that you make fairly simply. It allows you to just approximate it, whereas if you want exact values, you need to find the partial derivatives of the function that you're using. Now that's possible, and you can put these in, but that's not what we're going to do right now. Okay, so we have these points. Our main point over here, f of s and t, or p of s and t, as it is in our program. And we have point plus step 1 over here, should be on the right, our point plus step 2 on the left. Now, we could just use this. We don't necessarily need these other 2 points, but to get a better approximation, I'm going to use these other 2 points. So I'm going to go, so I added step 1 to s here to get from main point to over here to our next point. And so to get back over here, I'm going to subtract it. I'm going to subtract step 1 from s to get over here. And to get from main point to back over here, I'm going to subtract step 2 from t. And that will give us 2 lines and 2 vectors ultimately to make this normal vector. So I'm going to write a function, and I'm going to start doing this. Now, note the names of these points. It's going to be called right, left, and up, and down. So for s plus step 1, we're going to go right, s minus step 1 left, t plus step 2 up, and t minus step 2 down. Okay, so we're going to go back to the top here. That's probably a good view for it. And visible. Okay. What should I name this? It shouldn't take too long. Let's just name it normal. Even though we're going to be doing something slightly different than normal. Nope, I can't use the name normal because I'm probably going to use that in the function. Let's call it thickness, because it's going to add thickness to our parametric equations. So we need S T step 1 and step 2. Yep. Okay. So let's start. We're going to use the let function in OpenSCAD to allow us to make other variables within our function, just to make our lives easy so we don't have to write a million functions. We just write one function and we can calculate all the values. I should add a semicolon. Looks a little confusing right now. Don't worry, it should work out. So let's start with this point, right. So we're going to say right is equal to P of S plus step 1, comma T. It look nice. Okay, so right, P or F, P or F, whatever, of S plus step 1 and T. And that is what we have here. Oh no, that needs to be a comma. Okay, now left, we do the same thing. We go to the other side, F of S minus step 1 and T. So S minus step 1 and T. I can better work out the spacing here. Okay. Now up is equal to F or P of S and T plus step 2. And T plus step 2. And down is equal to F of S and T minus step 2. So, fairly predictable in a way. Maybe, maybe not. I don't know. I think it is. Okay. So now we have right, left, up, and down. Now we need to actually go to another picture that I've made. So we have all these points, and now we need to get vectors from them. I mean, they are technically vectors, but we need the right vectors, and just them on their own are not the right vectors. Okay, so this vector here, we're going to call it vector right, corresponds to this vector, because it's going to point in this direction, like that, like this. This vector, vector up, corresponds to this vector here. That's going to point in this direction, and this vector, the normal vector, will be the cross product of the two, and it's going to point up like this one. Okay, so vector right is right minus left, so this point on the right minus this point on the left. Let's do that. Vec right is equal to right minus left, and OpenSCAD is nice because it lets you do some mathematics with vectors, three-dimensional vectors, which can be helpful in situations like this, so you don't have to index into all of them. Okay, and then vec up, so vector up. Let's go back and reference. What is it? It's up minus down. And there's some mathematics involved to this and why these give us the right vectors, but I'm not going to go into that. It's just I think it's a little too much for this just one video. So hopefully you already know some vector mathematics, and I apologize if you don't. But you can just follow the code and it should work out fine, and you'll still be able to play with it and use it. Okay, so up minus down. Okay. So now, now we have all of these. Now we need the normal vector. We need this one. And as we can see here, it's vector right, and you take the cross product of vector right with vector up. So what we do, there is a function OpenSCAD, so normal. That's why I couldn't name the function normal. We are going to take, there's a function called cross. And so we need vector right and vector, vector up, not the whole one. Okay, now we have that. Now we have this vector here, and there is an additional step that I did not draw into here. Now, when we take the cross product of these two vectors, we somewhat know reliably how long this vector is going to be, but it's going to be a certain length, and we want this vector, for our purposes, to have a length of 1. So we need to normalize the normal vector. That process is called normalization. So what we're going to do, there's another function called norm. So we're going to call it a unit norm, which is the normalized normal vector. So we can just use this mathematics. This is a little confusing, I'm sure, just because of all the names. But essentially, so we want this of length 1. It's called the unit norm when it's length 1. So unit norm, this is going to be of length 1. This is not of length 1. So we take it and essentially divide by its length. So this function here, norm, takes the length of normal. So we divide normal by the length of normal. That's all that's happening. Okay, and what we want is the unit norm. So we return the unit norm. Cool. Now we need to do something with this function, thickness. We spent all this time working on it. We're going to have to do something with it, right? So we need to incorporate it. And how I incorporate it is going to just take me a moment. All right, so we need more points. So essentially we need a few more sets of triangles, kind of. But just to show you what's happening with the normal vector, I'm going to just do an example. This is not, this isn't going to stay, but so we're going to use a variable called length. I'm going to put it here. And this is going to correspond to the wall thickness. I probably should have used the word thickness for this, but I already used that because I couldn't think of a name for this function. So we're going to call it length. So length, which will be the wall thickness of our shape. Why don't we say just let it equal 1 for now? Okay, maybe fancy. Let it equal 2. See what happens with that. So length is equal to 2. So we essentially just need the same thing as this. But we're going to use this function, and we need to incorporate this. So we take away this, we need thickness, and we need S and T. We need step 1 and step 2. Okay, so this should do something. Now we need to multiply this by length. Just so that, if you remember, this function returns a unit normal vector of length 1, and we want to say how long it's going to be. So now length right now is 2, so this should be a vector of length 2. So when the distance from this, our shape to this new point should be 2. So let's see what happens. And that generated a bunch of points. And I'm starting to see that this is probably not a great function for an example like this. Let me see if I can make the squares a bit bigger, which I can because I added a parameter to do that. And it's a little small. Let me see if maybe 5. Okay, maybe 10. This is uber confusing to look at. So I'm going to keep trying some parameters until I get the right shape. You know what? What if I just change this function? So make it simple. See if I did the right functions. I know what I'm missing. I forgot an important part, and go figures. So the reason we're getting strange shapes, which are no doubt interesting, but not what we're looking for, is because I forgot to add the original point back to the unit norm. And so that actually needs to happen, not there, but here. So, I need P of S and T, and I need to add them together like that, like so. And that should do it. And I get an error. Of course I do. Why do I get an error? Because little s doesn't exist. Need big S. There we go. Okay, and perfect. Would you look at that? A bunch of normal vectors facing in. Not at all what we want. Not at all. Well, kind of what we want, but to get this quite right, we might have to add a negative sign. And that gives us the outside vectors. I'm not exactly sure. I know it kind of just depends how things are. But what we can do instead of making this negative is we can just switch these values. You can kind of switch them or change the negative depending on what you want. That should give you the same thing. There we go. Yeah, it just gives the same thing. And we get nicely approximated normal vectors, and it kind of looks fuzzy, which is interesting. And let me see if I bring back S, what we get. Yep, that's so much better. Okay, yeah, that's what we're supposed to get. I guess I need maybe at least one mistake per video. Yeah. And it's a length of 10. We don't need that, so let's take that down to 5. Yeah, okay. Cool. So now that I've demonstrated that and found the errors that were in my code, I need to show how to make this useful and add it on. I can just maybe, okay, so alright, so now we just have the points as opposed to the vectors, and this is correct now. And so what we need to do is essentially just remake these. So what we need to do is unfortunately copy this. 2 more times. And we need S2 and T2. So we'll call this level 2 triangle 1, because it's gonna be outside, but if you remember from the images, it's just triangle 1, but it's been moved up by this normal vector. Okay. I need to stop talking about it. There we go. Okay. So we have added the length times the thickness, and you could potentially just add length into the thickness function if you wanted, just adding another parameter here and then multiplying by the unit norm at the end, but I'm not going to do that. I'm just going to leave it like this for now. So we have S2 and T2. Now I'm a little all over the place. There we go. Okay, so now, as you can see, we have another set right here of triangles, which is cool. It's what we're going after. And the lower triangles, and they kind of both look like lower triangles. Anyway, so we got that set of triangles, and now we want the next set of triangles. So we'll copy and paste this. It's triangle 2. And so we have these points are fine, and we need both S2 and T2. Okay. And cool, we have essentially now like two I do not know why there are gaps here. That shouldn't be a thing. I guess we'll have to see how it goes. But we essentially have two, not exactly parallel, but side by side things. That's a little weird. Okay, I know what it is. I made a stupid mistake because of copying and pasting code, and that is one of the worst things that you can do, but I did it, so I need to fix it. I did not add the things in here, and that's why I was getting gaps, and it's stupid, and I have to do it. There we go. There we go. Wonderful. Now we're just getting artifacts, which are so much better than gaps, right? Probably. I don't know. Anyway, cool. Now we have two kind of parallel surface hulls of a parametric surface. And now we want to join them together. So how do we do this, you may ask? And if you've seen previous videos on surface hulls, you might know how to do this. But essentially, we're just going to take this whole thing, cut it, and stick it in our first triangle. And we can get rid of the whole portion because they'll all just hold together, and just be a happy hold family. Okay. But it's important to note that this is the main level one, and this is the second level one. That's had the normal vector added. So let's see if that makes it interesting. Oh, okay. Well, that kind of works. And if I make this part transparent, can I do that? Will it let me? It will, yes. So we can see that the bottom triangles have joined together and added thickness. And now we'll do the same thing here. Okay, get rid of the hull. Oh, no, we want that to give us information. Okay, so if we press F5, boom. Now the whole thing has thickness. And what we can do to make it pretty and nice and seeming like a surface or an ideal object is change the cube size to be really small. We can do that. So now you can't really see them. They just kind of look like segments. If you zoom in really close, you can see them, but it's still kind of hard to see. And we can increase the step size. It's going to take a moment to load. There we go. Better, still has artifacts. That's one of the issues with this technique. It sometimes generates like artifacts like this. And now we can change the thickness as well. That's kind of a cool part. Cool. Yeah, that's mostly it. I'm gonna take this back down so maybe I can add in some color. So yeah, that's that. Maybe I'll make a bit of a more, I'll try a little harder with the function. S times S T cubed. See what we get with that. It's strange, but not necessarily the most interesting. Times S times T. Okay, that kind of works, and let's add some more thickness to it. Like that. There we go, and now let's color it. Add some colors to make it look interesting, or sort of wing-looking shape here. So we probably want to color it one triangle at a time. Or we can just color both triangles at the same time. Oh, that's fine too. It might make our life easier just for now. So, yep. Okay, so we know that they go from -1 to 1, and we're multiplying by 10. So I guess in the most extreme case where we add a step, we might get to slightly over 10. So we can potentially use 11 as a divisor to make sure that everything works. So let's say ABS S. Actually, you know what? S just goes to 10. In the largest case, we can see, because this goes to 1, that'll go to 10. If I was concerned about step 2, then I'd use 11, but I can just use 10. So say over 10, ABS T over 10. Okay, ABS S plus T, and in the worst case that can go to 20. Divide by 20, and well, if we want to make it slightly see-through, a 0.5. Just throw in a 0.5, the alpha. And we have color. Kind of looks like a watermelon. I think that will do. What if I want to make it slightly more vibrant? That's not bad. Yeah, that's pretty much the how you do the surface hull on parametric surfaces. That's the whole thing pretty much. That's we've gone through it all. So yeah, we started with the functions, then we did a hull, and then we moved on to this this function here, and we looked through our drawings to see how to do the hull, to see how to get the normal vector, to see again how to get the normal vector. We defined our steps, our for loop, the hull. We have two major hulls. There's this hull, which is the triangle 1 still, level 1 and level 2. And we have the second major hull, triangle 2, the level 1 and the level 2. And then we just added color over here. And that's pretty much everything. So yeah, that's it. Thank you for watching, and hopefully I'll see you in the next one.